Dr. Jason Box is a professor of glaciology and climate at the Geologic Survey of Denmark and Greenland. Since '94, he's made 30 expeditions to Greenland and to install and maintain measurement networks on the Greenland ice. And he's lead author for Arctic Monitoring and Assessment Program. He's a contributing author to the 3 recent Intergovernmental Panel on Climate Change Assessment reports. So these are major global reports that bring together all the latest science on climate change. And he's an outspoken advocate for climate change risk management. He specializes in satellite observations of snow and ice. And he did this all by starting out in Boulder, Colorado, the University of Colorado, in geography and atmospheric and oceanic science, where he taught then at Ohio State for 9 years, teaching intro environmental studies, and then moved to Denmark to take his current post. And I also hope he doesn't mind that I share. He's coming here to the US to talk with you all en route to surprise his mother for her birthday, which is very sweet.
I want to thank the organizers and thank you all for being here tonight. And I'll just get right into it, talking about mostly Greenland ice and the connection with our global climate. So this story began for me age 17, 18, undergraduate. I wanted to study astronomy and computer science, and took a course where I saw these curves of important atmospheric chemicals shooting upward with industrialization. So this is the book that set me on that journey, because instead of studying astronomy, I realized there were problems on planet Earth that I wanted to be part of addressing. And in the pages of that book, I worked out that we were, at that point in time, 29% elevated CO2 in the atmosphere above pre-industrial. And today we're more than 50% elevated, some 31 years later. And my enthusiasm somehow got the attention of a Swiss professor at the University of Colorado, who, as an undergraduate, I convinced him that I should come along and help at this research camp, now known as Swiss Camp. And this was a useful calibration site for satellites, because the surface is homogeneous. The sky is relatively clear of clouds over the Greenland ice sheet, and we were making ground truth measurements for satellites. This was at the beginning of what NASA called the mission to planet Earth, to turn its sensors onto the planet instead of so much just looking at other planets. And so it was NASA that sponsored this work. And there I am, age 20, in Greenland at the time, thinking, well, this would be a once-in-a-lifetime experience. And I was naive enough to not realize that I was starting a career. And that supported my graduate studies, where I was the lead installer of what became a network of automatic weather stations like the one that you see there. And this mast has a number of instruments that were designed to get closure on the surface energy budget. There's energy coming in primarily from the sun, but also from infrared energy coming down, and heat from the atmosphere. And that's balanced by energy radiating upwards, reflected upwards. Evaporation cools the surface, and we got closure on this energy budget and also the so-called mass budget. There's mass coming in from snowfall, rainfall, and mass is exiting by meltwater runoff and the flow of ice toward the sea. In a stable climate, these balance and the shape of a glacier stays constant. And in the 90s, the climate change issue hadn't expressed itself in a way that was recognized by science until 2002. So I was already 8 years into the work at the point in 2002 that Greenland Ice started grabbing headlines. So for me, success was tied a lot with the timing of getting some expertise prior to the issue becoming so popular and competing with so many other important issues around the world. So these were something like 18 stations that we installed. And this is how we started at the one site, Swiss Camp, and then began to expand it into a network by driving away from Swiss Camp. And this is to illustrate how no one said it would be easy. And some of our stations would melt over, and we would pull all-nighters to get the equipment running again. And in the morning, there's Professor Conrad Steffen talking to the BBC, who were coming to the camp later, and this was the moment when the science became mainstream for Greenland. We were taught up until that point that the Greenland ice sheet was frozen at the bed, and that meant that it had tens of thousands of years reaction time to climate change that we knew was coming. But the epiphany was that meltwater draining to the bed meant that the bed of the ice sheet had the capacity to react much more quickly to increased melting than we had thought about. And I'll talk more about that. I wanted to mention the 9 years I spent at Ohio State. And in addition to sharing about the workings of the instrumentation, teaching introductory environmental science gave me a broad spectrum in environmental issues that I could talk not just about the weather and the clouds and the sunlight, but also about the connection with social science and the geography of environment. And after 9 years and my experience in Greenland, I was recruited to Denmark, and so we took this adventure of moving to Denmark to assist the Danish government in installing and operating a complementary network. The red circles, you can see they're focused in the lower parts of the ice sheet around the edge where most of the melting happens. Because really in the 90s, the question was more about how much snow falls on Greenland, and melt wasn't in focus. I remember an Australian scientist asked us, like, wouldn't you also want to be studying how much melting there is, not just how much snowfall? And he was right, and that was part of this story of how science learns about nature. We have to observe nature, and then eventually we bring important factors into focus. I wanted to show this next version of the Danish equipment. I could eventually convince my colleagues to put a rain gauge on this kind of tripod, and when we did that, and we've deployed them all over now, we find that this is that's actually a temperature record, but I meant to show you a rainfall record. In a lot of those instances when the red colors, when the air temperature was above melting, there was rain falling. At this location and others, This particular site is more than 9,000 feet above sea level, and so rain is a not uncommon phenomenon, even high on the Greenland ice sheet, and we didn't appreciate that until we started to measure it. And so here's a temperature history of the last 50 or so years, 70 years, where I'm sure you've heard by now that the Arctic is warming faster than the rest of the globe. The global temperature is the blue curve on the bottom, and you'll notice that there's actually a widening difference in the slope of the red curve, the Arctic average temperature. And that has come into focus just in the last few years. Oh, the Arctic is warming so much faster. If we go back to the 1990s, you can see how around the middle of that curve, the Arctic temperatures had not yet really separated from the global pattern. And it's important to remember that in the 90s we lacked that perspective, but now the Arctic temperatures are so much above their previous envelope that you read headlines, the Arctic is warming more than 3 times faster than the globe. Here's a map of that same data, and you'll see from 1950 onward, it's racing forward. We're in the 1980s, and these are temperature anomalies. So the red colors are temperatures above average, and this average is from 1951 to 1980. Another map looking from the North Pole downward, if you will, at the Arctic. This is the annual temperature change over the last 44 years. And you'll notice that the most warming is in the Barents Sea, north of Norway, Sweden, there. And that's in a place where the Arctic sea ice on the Arctic Ocean has retreated a lot. It's also a place where the warm current of the so-called North Atlantic drift terminates just south of that Norwegian island of Svalbard in the Barents Sea. So this is the hot spot, really. But you'll notice overall a warming pattern. There's more warming offshore, again over the Arctic Ocean, where sea ice, this thin layer, it's just about a meter thick of ice, that has lost half its average thickness in the last 50 years and has retreated an area several times that of California. There's more heat release into the atmosphere because that sea ice cover insulates the atmosphere from the ocean. The ocean is, of course, not colder than -2 or so, and so when the sea ice is not there, the ocean is radiating a lot more heat upward. That's part of the signal. This graph shows several different factors. On the far left is the albedo. That's Greek for the whiteness of the surface. And when you remove sea ice cover or snow cover, the background ocean or land is much darker. And melting will expose a darker surface, leading to more sunlight absorption, and that amplifies the warming. The next 2 leading factors, the lapse rate and the Planck feedback, have to do with the temperature profile being warmer near the surface, so temperature versus height. The lower atmosphere is warmer at a given elevation than it was in the past, and when there's any water vapor especially, and that's the 4th element, those second, third, and 4th elements actually work together to radiate more thermal energy downward. And so these feedbacks, they amplify the initial effect of warming. And these are why the Arctic is warming so much faster than the world. the loss of sea ice that lets more heat into the atmosphere from the open ocean, the darkening of the surface, absorb more sunlight during the sunlit period, and then again the effects of a warmer and more humid atmosphere radiating more infrared down to the surface. Those are the main factors. Back to this map of the temperature change. Okay, so here's the snowfall change. The green colors are where the snowfall is increasing, say over southeast Greenland or the Barents Sea north of Norway, Sweden. And I wanted to put this question out, and that's why I repeated this slide before. Okay, it's warming over the Barents Sea. It's warming over the North Atlantic, say north of Iceland. Who'd like to tell us why there's less snowfall in a warming climate? Rain instead, that's it. And so this is the rainfall change map. There is a lot more rainfall happening across the North Atlantic. In a warming climate, there's more humidity. This has been confirmed with multiple independent measurements like weather balloon data over decades, satellite data over decades. It's a wetter Arctic. So a decrease in snow cover at the expense of increasing rainfall. And this is the overall precipitation change. That's the snowfall plus rainfall, total precipitation. It's a wetter Arctic, especially over the Barents Sea, especially south of Greenland, the Norwegian coast, actually practically everywhere. Okay, Greenland, dome of ice, the world's largest island. I like to call it the world's smallest continent. It has an average elevation of, 1,500 meters. I think that's about 4,000 feet. That's the average thickness of the ice. It has enough ice to raise global sea level 24 feet. This has a vertical exaggeration of a factor of 10, so it's not quite that steep. I wish it was more skiable in that sense, but and let me take you to West Greenland. This glacier that we're looking at here is the world's fastest continuously flowing glacier. It produces 50 billion cubic kilometers, 50 billion tons, 50 gigatons of icebergs per year. To put that into context, Los Angeles uses 1 cubic kilometer of fresh water every 2 years. So it's 100 times the Los Angeles water usage per year is being pushed out of this thing. It is the world's fastest glacier. And as you can see, the front of this glacier has retreated quite a lot in recent years. And I've got some pictures. I shot this in 2002 when there was still an ice shelf on the front of this glacier. This area of floating ice, this ice shelf, is 1.5 times the area of Manhattan Island. And we were surprised, here it is again, we were surprised in 2005 that it had begun disintegrating. We actually didn't recognize it on one time over. We're flying to Swiss Camp. Swiss Camp is just 10 miles north of this place, inland. And if you can make out on the left side, there's a lagoon. This area here, this was solid ice. It wasn't really moving. The ice is pushing out here. It actually has a native name which reveals that it was ice-free in the past, actually. Here it is opening up again. So now the ice broke out of here at the same time that it's retreated. By now, the front of this world's fastest glacier has retreated by more than 10 miles. And it did so over the period of 10 years. And because of the reduction in flow resistance that the ice shelf was providing, a buttressing effect, this glacier doubled in speed. It went from flowing at about 10 kilometers per year to almost 20 kilometers per year. It's about a football field per day that this is now discharging ice into Baffin Bay. And here's a video, real-time, shot by a 13-year-old on air safari tourist flight, and you can see a mountain-sized iceberg breaking away. It's so large in real time here, you can just barely make it turning over, because the cliff on the front, it raises up to 300 feet above the sea level, and the thickness of the iceberg is 900 meters, something like 2,000 feet thick. And actually, if we let this play, it's quite a long video, actually. I think I can drag this forward and speed this up a little bit. You can see actually the full thickness of that iceberg. It's on its side now. And if I rewind, I don't know if this is that helpful, but you can see it's turning over. I'm scrolling forward now, and it's turning onto its side. There you can kind of see the full thickness of this thing. So it's quite a tall berg that is fallen over kind of like a domino. And this goes on, I guess. And I'm going to go forward, and then you get this basal ice that's under such pressure that the air bubbles are squeezed, and the gas goes into a clathrate. The bubble gets squeezed into a different chemical form, and you get that sapphire blue ice. But the main point I wanted to make here is, in a matter of minutes, a large length of this glacier can break away, and it takes much longer for that ice to build up. And we can see this in sea level records, how sea level drawdown, as the ice sheets build up, it takes much longer than a sea level rise can happen. It's a kind of a sawtooth pattern. A gradual sea level drawdown and abrupt sea level rise. And the ocean sediment records record it on a 100,000 year cycle of ice ages, this same pattern of faster sea level rise and slower sea level drawdown. To take the story forward, it's useful to follow the water, and it's kind of like, if you want to understand how things are working in politics, you follow the money. Well, here, to understand how glaciers work, let's follow the water. And the story can begin at the surface of the ice sheet, where the melt rates have more than doubled in the last 50 years. This lake is 1.4 kilometers wide. It has 30 million cubic meters of water, and melt lakes like this are natural. What appears unnatural is the lakes are forming earlier, they're forming higher on the inland ice, and this graphic illustrates Western Greenland. It's a satellite mosaic of the numerous lakes that, as you can see, act as kind of solar collectors because they're darker. And we've measured that the ice is melting about 30% faster when the surface is flooded. So they represent one amplifying effect that is not in the models used to project sea level into the future. The lakes also drain. Very few of the lakes stay full through the melt season. There's an abundance of cracks, and eventually the water will find a way to rapidly drain into the ice. And so the next point on the follow the water journey is this water having a temperature that is several degrees warmer than the ice sheet internal temperature has a warming effect internally on the ice. The water infiltrating in transfers heat to the water, it melts ice, and the internal heating in the ice sheet has the effect of warmer ice can deform more easily than colder ice. And so this softens the ice sheet and allows it to flow or to deform more easily. This effect is not yet in the models used to project future sea level rise. Back to the surface, there can be algal blooms. These are also natural. What appears to be unnatural is the duration of the algal blooms can be greater. The bare ice area is greater. The duration without snow cover, the bare glacier ice underneath is greater. So this is the albedo feedback, this darkening feedback, also not in the climate models used to project future sea level from Greenland. The water makes its way to the bed, and the big discovery in 2002 was that the water at the bed, because water is incompressible, can lubricate the movement of ice over the bed when the water is present, speeding up the ice 100% greater than it would have otherwise been flowing. This melt-induced flow acceleration is not in the models used to project future sea level. Same water then makes its way out into the marine environment. So this is Baffin Bay in the foreground. This is the Arctic's widest glacier. It's 100 kilometers wide of marine terminating tidewater glacier. And it's a little bit difficult to see, and maybe the next slide you'll see that this water is sediment rich, which is clear evidence that the water has been communicating with the bed of the ice sheet. And in this video, you'll see this is kind of muddy waters. Again, the water has been communicating with the bed. You'll notice this embayment, and where the ice is breaking away is focused where the water is coming out. And so it's pretty obvious that there's more iceberg calving, more fracturing where the water is coming out. And when the sun shines on the water surface, I think you see that in the next slide, you can see just how turbulent the water is. This convection is a much more efficient way to transfer heat between the ocean and the glacier front, and that provides an enhanced melt mechanism that is illustrated here. At depth, below about 300 meters or 1,000 feet in depth, these are red arrows to illustrate relatively warm water. The water temperature there is between +3 and +5 Celsius, the melting point at 0. So what's happening is the water that's flowing along the bed then rushes upward because it's fresh water, lighter than salt water. It rushes right along the front in trains, warm, so-called Atlantic layer water, and causes melting right at this place called the grounding line, where the ice loses contact with the bed. This is all underwater, and forces heat exchange right at the front. So this has a very effective melting mechanism that connects the amount of meltwater produced at the surface with ocean temperatures, which have been increasing. This effect is not in the climate models used to project future sea level rise. Yet another effect not in the models is hydrofracturing, the fact that water is heavier than ice. The only condition necessary to open up pre-existing fractures is to keep this crevasse filled with water. And so the hydrofracture process, in my opinion, is responsible for this breakup. This was the Arctic's largest ice shelf. The width here is 10 miles. The height of the cliff on the left is 2 Eiffel Towers, and this broke away in a single year, and that was 246 square kilometers. That is almost 3 Manhattan Island size areas. It broke away during a record warm summer of 2010. So I mentioned my opinion is that hydrofracture broke the Arctic's largest ice shelf, and 2 years later, the next piece breaks away, also in a record warm summer. It's been hard to prove that warming broke this ice shelf. We tried to do it, but let's just say it's Jason's opinion that it's hydrofracture. Now back up to the surface. We're still following the water. This was a surprise. A colleague of mine shot this video, and instead of a bright white snow surface, you see a lot of meltwater flooding the surface. This is at an elevation where on that date it would normally be snow covered. And this August 2021 melt event drew our attention. So here's a sequence of satellite pictures that show, as we're going inland, meltwater and clear evidence of surface flooding. We could see this in the satellite pictures. And we studied this thinking that rainfall was going to be the main part of the story, but it turned out it was the heat in what are now well known as atmospheric rivers. You've heard about these in the news a lot. California is getting dumped on right now. My friend in California let me know he said we're getting nuked by snow today, and it's crushing the roof on his house, actually. But in the red colors, you see a concentrated poleward flow of water vapor and heat. And after studying this, only using measurements, observations, no models, we concluded that the most important thing, even though it was raining at the highest point of the ice sheet, the first time ever observed, you probably saw those headlines, rainfall witnessed at the highest point of the Greenland ice sheet. And despite all the millions of dollars of equipment they had at the summit of the Greenland ice sheet, they had not a single rain gauge. But we had some rain gauges up at the South Dome there at 9,000 feet and recorded some rainfall. It was a few millimeters. It turned out not to be the real story. The story here, in addition to the atmospheric rivers delivering heat, was the darkening effect that heat had on the snow cover. And you'll see that kind of now. I'll just run that again. Bright white, is it running? And then it's going to get a bit darker. It's a little hard to see. The story became that because ice crystals and snowflakes, they have really jagged edges that scatter light. That's why the snow is white. It's all the scattering of light across all the colors of the spectrum. But melting will round the ice crystals, and the rounder grains reflect less light. And the story here was that after the rainfall had ceased and the atmospheric river had blown away, the surface was darkened. The sun came out, and it sustained melting for another week. And it produced the largest melt for so late in the season. This is the end of August. It should be returning to winter conditions, snow cover, but melt was sustained in August of 2021 for an additional week or more, and that was just that much more melting coming from Greenland. Our measurements of the surface, so we lay out all these recorders, and we're kind of dumb. We don't really know what nature is doing until I say you listen to the data. You just look at the numbers, and then you're like, oh, that's what the ice is doing. And thanks to all of the measurements from satellites and on the ground, nature reveals its secrets. We just have to listen, observe, open our eyes, and that's the latest what we learned. September of last year, another atmospheric river. So the red colors are where the temperatures are above melting. And so you can see here in early September of 2022, we have above melting temperatures high up on covering Greenland, and according to satellite microwave measurements, which can see through the clouds, we could see that this was the latest that there was that much melting on the surface of the ice sheet. More than 1/3 of the surface was wet, and so late in the season. So this was a new record set just last September. This is the water vapor, and it's just in yellow. That's where there's the most moisture. You can just see for yourself the atmospheric river. It's a model behind this, but it's driven by observations from aircraft, weather balloons, satellites. So this is our best way of being able to measure. And these are every 3 hours. Actually, these data exist every hour. In my Arctic climate classes, the story was there's no data in the Arctic. There's no data in the Arctic. That's completely changed. We have so many satellites, and we've got 40 stations, measurement stations on the surface of the Greenland ice sheet. So now it's more of a problem of too much data. And so we get into fancy data science here so that we can visualize and understand what's happening. So it's a completely different story now. We have a lot of information. And we were on the ice sheet in September. This photo on the 1st of September last year. We were concluding our work on the southern Greenland ice sheet, and there were these ominous clouds. These are recently named, officially named asperitas clouds. Maybe you heard the news. It's a new cloud type, and they've always been there, but they have a rolling underside. The title slide had these, and they're associated with kind of intense weather. And we knew that there was weather coming in, so we rushed off the ice. Our plan was to walk off. It's a little bit greener to walk instead of fly, and it's also kind of fun. And we had an artist along because we're constantly experimenting or developing new ways to communicate about what do we observe. And so bringing an artist with is yet another way. And so we made it off the ice into this place I called Nevada, because it was quite warm there. Well, not on this day. This light brown rock, and we had brought her painting equipment, her easel and her paints, and while she was painting this, it was raining, and so she's painting this glacier. It's raining onto her canvas. I don't know why she chose to use watercolor, but it actually really worked, because you can see the paint is dripping down the canvas, and just the chance that it was raining, that her painting is about the interaction of rain and ice and water. It all came together at that moment to produce this totally unique painting that tells that story of the connection between ice and rain and climate on a record-setting warm day. So I'm really proud of her, and I think we totally got what we were looking for on that day. Now I'm going to shift back to the Arctic versus the globe, and here's a movie of the jet stream. Natural to have the jet stream, and it's a fast river of flow in the upper atmosphere, and the speed of that river depends on the Arctic being colder than the rest of the globe. If there was no temperature difference, there would be no jet stream, at least not like that. And as you know, the Arctic is warming faster than the globe, so the temperature difference that the jet stream depends on is getting less. And what that's doing is making the jet stream wavier. So you count the wave numbers, up, down, that's one, up, down, up, down. So high wave number events are associated with so-called climate events, extremes. This was the typical pattern over several years where you had a cold winter and a high and dry West Coast. So California has been having this drought, and the politics were convenient because the politicians could say, where's the global warming? When they needed to look only to California to understand, well, it's about persistent weather patterns. And you may hear the weather people talk about this ridge. You know, they say this is a ridge, meaning this shape. And so it's been called the ridiculously resilient ridge. And so you have a high pressure here, warm, dry, high and dry out west. This pattern of the jet stream, otherwise known as the polar vortex, getting wavier, getting more stuck, lazy pattern, a more slowly moving jet stream has become the signature, or one of the signatures of Arctic climate change. And that's the effect that Arctic climate change has on the weather down here where we are living. You'll remember the record warm Pacific Northwest. They had 120 Fahrenheit in Vancouver. Remember that a couple of years ago? This was a ridiculously resilient ridge that was pumping warm air up to the south, but from the south. It's stayed like that for a long period of time, and that's a typical climate change pattern, if you will. It's been called an omega block because it looks like that Greek character, omega. Europe, 2019, had record-setting temperatures because of this omega pattern being more persistent. The planetary wave, the jet stream, was producing a high-pressure ridge that was pumping up heat from the Sahara up to France, and you had 110 Fahrenheit in Paris. 2022 was a similar story, these kind of purple colors. It's 110 Fahrenheit across Spain for a lot of the summer. And you heard about the fires and France having fires. The continent of Europe has really been feeling it. And when the Rhine River in Germany dried up and the Loire River dried up, that's when no one could ignore this heat wave. It stopped the transport of coal. All the barges that move so much around Germany, it was stopped. So it had economic shocks that combined with Putin's war, and Europe has been having quite the economic crisis ever since. This confluence of multiple bad things happening have led to an inflation crisis in Europe. And there's actually a lot of science which is showing that as the temperature difference between the Arctic increases, this study links a wave pattern. So here's Europe, and these are breadbasket regions where in Russia, in North America, where grain is being produced, that this is threatening the grain productivity of the Northern Hemisphere. Arctic climate change is connected to what's a growing risk of food price commodity spikes, of inflation, of real hunger. If you remember, summer of 2010 was the warmest on record in Russia, and they halted grain exports. And that produced a global food price commodity spike. It was even connected with the so-called Arab awakening. What became known as the Arab Spring Revolution had an element of drought, and that triggered that revolution, combined also with drought in Syria. That civil conflict was connected, and so at a time when we need global harmony, climate change is destabilizing states. It's making it harder for us to take forward the global cooperation that we need to tackle the climate crisis. Back to the ice. This is a bar chart with the different ice contributions to global sea level, and Greenland is in this bar. So Greenland is the largest single regional source of sea level rise. Antarctica, despite being 9 times larger in area, is still not yet the leading factor. If you add up the different ice contributions, ice is the leading cause of sea level rise. There's people extracting groundwater is a source of sea level rise, as is thermal expansion. A warming ocean occupies more volume. So all of these come together into the sea rise issue I realize you know quite a lot about. This chart, there's thousands of years on the horizontal axis. This goes back 20,000 years. So out of the last ice age, we have a huge sea level rise of 120 meters because of the collapse of the ice sheet over North America, primarily. And then we have a period of very stable sea level lasting for thousands of years. This is about 6,000 years, the so-called Holocene. And that very stable sea level was very convenient for the development of civilization because seaports don't move around. The sea level is always conveniently where it was yesterday. And that is an important factor in civilization's story. The future is somewhere in between these curves, and it's going to take a lot of time, or some time, for Big Bend to get flooded. But that catastrophe has begun. And of course, the question that we always get is, you know, how fast is it? And because, as I explained earlier, the models aren't up for it. We can only observe and say, well, the models don't have this, they don't have that, they don't have this. So these curves here, we can't tell you how quickly this will happen. We do have the past, and there have been some abrupt sea rises, you know, here and here kind of thing. It's still a bit fuzzy, so the science community cannot yet tell you what the sea level will be like in 50 years. But we have our best guesses, and that's what I'll talk about in the last few slides I have here. Okay, this is 2016. New York Times declares the sea level rise era has begun, and I think by now it seems like we've gotten the memo. We all know that sea rise is happening. But I got some more detail about that just by being here in Chestertown, looking out the window, and then just pulling up the Annapolis tide gauge record. And noticing that, well, there's been 30 centimeters, a bit more, since 1930 of sea level rise in Annapolis. And the average rate is 3.7 millimeters per year, every year. Another 3.7 millimeters. It's slightly larger than the global rate because of some ocean current changes, but there it is. There's the observed rate. And here I am on Waterfront Street, and I was out there this morning looking out the window, and I was like, gee, that sea wall is, I measured that 16 inches. The ocean is only 16 inches, and then I came out later at high tide, and the water was all the way up here. And I'm looking at this house, and I know those that live here, you know this issue. This issue is becoming now, it's a nuisance now, and what can we expect for the future? You've probably seen these curves. These are the observations, and then we have different scenarios. And of course, the high carbon emission scenario is here, the global harmonious cooperation scenario is here. The get off fossil energy is here. The windmill and solar revolution curve is here. But what these curves, they're actually deceiving because, as you probably know, storm surge can produce this much additional sea level, and that's what flooded the New York subway under Sandy, Superstorm Sandy. $60 billion of damages to New York's, just because sea level only needs to be that much higher than the top of the wall to flood the subway. And so and in the same year, actually, different storm, Boston streets flooded as the second nor'easter in 2 months pounds the city. And so this here's the normal tidal curves, and then here's the storm surge. The storm surge is this guy. So the wind is pushing the water up. You already know this. I'm not telling anything you don't know. But it pushed, when the storm surge peaks at the same time as high tide, then you're way off the scale. And so these smooth curves aren't all that helpful, because all it takes is one storm surge to flood the New York subway, or to flood your basement, but I think it's remarkable. I sit there and I look at Greenland and I'm thinking about sea level, but I have to come to Chestertown to look out the window and realize just how close that is. So I don't want to completely ruin your Tuesday evening. So to try to lighten up here, I mean, we actually know how to fix a lot of this stuff. Whether we can implement that is another question. And what I learned today from Jemima is even more forward-looking. Jemima here at Washington College, it is to look at what has worked in the past. We know things that work. We know things that are compatible with our own career trajectories. And especially for the students, whatever career you're going into, you can find applications that are going to resonate with my last few slides here. In principle, what we need to do is to halt carbon emissions to the atmosphere, and we need to remove 200 to 500 billion tons of carbon from the atmosphere. We have to do both of these, and if we can do these, then we can stabilize climate. I make it sound so easy. But to unpack number one, halting carbon emissions, and I think this is common knowledge by now, we need to accelerate the transition to low carbon energy. Protect existing forests, especially old forests which have old soils, that the soils and the peats contain a lot of carbon. The last thing you would want to do is to deforest more than we already have. Reduce biomass burning. Concrete is a big producer of CO2, so these are really lofty, high-level goals, and I think I prefer Jemima's do what we know works. Do we know that using less concrete works? It's easy for me to say use less concrete, but we need to find ways. Removing a lot of carbon out of the atmosphere is a huge prospect under the name of CDR, carbon dioxide removal. And this can be achieved using this amazing technology developed by nature called the tree, called grasses, called peatlands. And so we don't actually have to invent a machine that does this. Well, we can invent machines that accelerate this. So-called direct air capture, the technology that nature has already developed over millions of years. It's called photosynthesis. That's pretty effective. I think that's what we should focus on. Okay, just a few more slides. I know it's a lot. I'm sorry. It's always hard to, which slides don't make the cut. I've got twice as many slides. They're almost as interesting. But this is quite interesting. We tend to focus on economy. Put the economy first, stupid, right? Well, it is kind of stupid because we should also recognize that energy and economy are linked. You can't really have an economy without energy. And, well, there are environmental connections between economy and environment. Like if there's a drought, you have problems with the economy, say. Environment and energy are linked through, say, carbon emissions to the atmosphere. That is changing our environment. But it gets more interesting in this systems perspective. Well, there's also equity. We should consider the fact that there's global inequity, and actually those that suffer most from the prevailing economic model are those least responsible for the problems. So we need to contemplate equity. And we can think of other E words like education. And that's one of the keys here. If people were more aware of these issues, and rather than living hand to mouth, they would be more informed to make good strategic decisions. All of this, we need to make big investments. And when you make big investments, you want big returns, right? Well, these returns are paid in resilience. We can weather those next shocks if we make these investments, and we can have a prosperous society by investing and planning and being smart and considering the system's perspective. And so I'll conclude there. Thanks for your attention. I could self-moderate just a few discussion points. I'd love to hear any comments or difficult questions from the audience. I saw the gentleman's hand in first. Yes, you.
You spoke about the jet stream and its effect on our weather. But with the amount of ice calving and water coming off of Greenland in the areas that you showed, which I think was the Jacobson Canyon Glacier and up past Eki and that area, that amount of water and ice coming down into the North Atlantic has to affect the Gulf Stream, and because of the relationship between freshwater and saltwater, can you talk a little bit about that effect and how that could relate to weather?
Yeah, the question was about all of this extra fresh water that's flooding into the North Atlantic, and the Gulf Stream is this flow of warm, salty water from the south along the U.S. East Coast up to Norway, right? And what I've learned about that is that the Gulf Stream is a wall that the freshwater cannot mix past. So what's happening is that freshwater from enhanced Greenland and Arctic Canada glacier melting is accumulating in the North Atlantic, producing a freshwater anomaly there that expresses itself as a surface cold, record-setting cold temperatures at the surface of the North Atlantic, while the rest of the world is record high, increasing temperatures. Can you imagine that? It's actually, you couldn't make this stuff up. The North Atlantic is record low temperature at the surface, and the world is record high temperature. What is the effect of this disruption of the North Atlantic ocean circulation? Well, basic meteorology, chapter 1 is that it will intensify storms because of the temperature difference of the warming atmosphere and that cold surface. It produces cyclonic vorticity, chapter 1. And we had in December of 2015 examples of these kinds of what James Hansen has called superstorms. Well, his superstorms are even more violent. But there have been examples of strong storms. We just had Storm Otto in Denmark a week ago. But whether those are caused or made worse by this, well, you actually can conclude they are made worse if that baroclinicity is set up. If the surface is colder, the atmosphere is warm, then it's not controversial at all that those storms would be stronger. Whether it shuts down the global thermohaline circulation, producing what was overly dramatized in the film, what was it, The Day After Tomorrow? That was amplified into a disaster film, but the premise has a basis in the fossil record. There have been abrupt climate changes in the past due to disruption of the global thermohaline circulation. So it is debated, and so my professional view is that it is a real issue. and that is not that controversial. But whether Greenland melting is making the storms in Europe worse is a bit more of a topic scientists like to debate. I'm pretty convinced it is. Will it disrupt global climate? Big question. There's active work on that. I just had a proposal turned down to work on that. Hopefully someone will make more sense out of it.
I guess in a simplistic way, I look at the ice melt that came off of the glaciers during the Ice Age, and how initially that water would have poured into the Caribbean. And when it got north into the Great Lakes, all of that fresh water had to go out through the St. Lawrence and into the North Atlantic. And it was somewhere that I thought of it, that spoke about its effect on the Gulf Stream and why we plunged back into a second ice age. So what I'm correlating in my mind at least is there that same effect of what you're saying?
Right. There is this historical analog when Lake Agassiz drained what's now Hudson Bay, drained her up abruptly in this so-called meltwater pulse 1A. And there clearly was a climate cooling from that, and that's what's expected out of this, what Wally Broker from Lamont Doherty called the Achilles heel of the climate system in 1979. But it hasn't yet been proven or demonstrated in a way that is convincing to produce a scientific consensus. And then behind the gentleman.
I guess we can agree that there is a tremendous amount of weight sitting on top of Greenland.
Tremendous amount of weight sitting on top of Greenland, yes.
Is there any effect to the elevation of the land as that ice and water pour off? Are you measuring any rise in the land?
Yeah, there's quite a post-glacial rebound, if you will, and I prepared a slide for that one because it's a really good one. That this is one of the sea level rise. It points so global average sea level rise occurs on the green line. That's where you get the average, but sea rise is not equal everywhere. And what this map illustrates is how actually the loss of mass in Greenland, this is gravitational effect alone, actually reduces global sea level rise to 50% of average, 0.5, around Greenland. That in the vicinity of Greenland, Antarctic Peninsula, Patagonia, there is less than average because of this gravitational effect. The main point here is it's not directly to your point about the post-glacial rebound, which has northern Denmark moving upward, and southern Denmark is just on that fulcrum. But here you can see in the tropics there is up to 50% more than average global sea level rise just from this gravitational effect. So the melting that's happening in the polar regions is actually raising the rate of sea level rise is greater in the tropics. And this is important for places like the rice basket of Southeast Asia, the Mekong River Delta, the Nile River Delta, Bangladesh, the Philippines, the Pacific Islands. So we are spared in the north some of the sea rise, which is focused in the tropics. Let's get a follow-up. I don't see other hands.
Just to follow up, what you're seeing here on the shore, in a lot of places, it's happening is there's
Subsidence, yeah.
The land is dropping, and obviously the water is.
Yeah. Relative sea level rise. Yeah, the Annapolis curve I showed was corrected for the relative sea level rise, so the isostatic movement of the land. And I wanted to ask you, because I think you know better than me, why is the land subsiding here?
I think it's the geological aspect of what we're on, a big sandbar. and we're just kind of floating.
But it's subsiding, so why? Because typically it's groundwater extraction that like in Jakarta, they've been pumping out water, and so the capital of Indonesia is lowering an additional meter because of groundwater extraction. Is that subsidence? Changing farming practices, the soil practices also affect sea rise. So it's relative sea level rise is actually quite complicated, but people in the field of geodesy, they're all over it. Let's hear from someone else.
Up top, Jason.
Oh, go for it. I can't see you, but.
Can I get my mic?
Yeah, I was curious. I've read about a couple of other proposals for reversing the global warming that involve geoengineering. One of them involves sulfur dioxide, and the other one involves creating more clouds over the ocean. Have any of those things been tried? This was a few years ago. This was written up, and I wondered if they've tried any of these things. You familiar with what I'm talking about? The sulfur. This is basically simulating what volcanoes do. They throw a lot of, the super volcanoes throw a lot of sulfur dioxide up in the stratosphere, and when Pinatubo erupted, that reduced the temperature temporarily by about 2 degrees Fahrenheit.
Yeah, that's right. And I reviewed a report that made a survey of all these various climate-altering technologies, interventions in, and then the most well understood and popular and seems to be cost-effective approach for solar radiation management would be to deploy, and it could be done at a relatively small cost.
Yes. Yeah.
As compared to the impacts of, say, drought on agriculture. And so for something like $40 billion a year, we could shroud the surface of the planet using stratospheric aerosol injection by a fleet of aircraft flying in the lower stratosphere, spraying out sulfate aerosol. So David Keith at Harvard has done this work for the last few decades, and it would probably work. What it wouldn't solve is it would give a justification to continue adding carbon to the atmosphere. It would get us hooked on the stratospheric aerosol injection so that if we ever stopped doing it, the shock to the climate system after that could be severe. It may also change rainfall patterns globally, so the South Asian monsoon may fail because of stratospheric aerosol injection. The topic has global governance issues all over it, so it's a geopolitical minefield. It is affordable. It probably would work, but again, would get us addicted to that techno fix, which would probably reduce our effectiveness of tackling the source of the problem, too much carbon in the atmosphere. So as you can tell, it's controversial to put it mildly, but would we need to use it in an emergency if other feedbacks like burning of the Amazon became out of control, the Congo, the Arctic tundra, if that additional carbon release into the atmosphere confronted us with the dilemma, do we get into stratospheric aerosol injection at an even larger scale than we anticipated to try to cool things off just enough to try to maintain the forests on the planet? Hopefully we can see enough of the warning signs that we already have in abundance to have a much more ambitious climate policy. And that's the kind of stuff that gets discussed at World Economic Forums and the climate ministerials, most recently in Egypt. And I've been attending those meetings and noticing you don't see enough policy at the global scale, because as you know, we have issues with global harmony and you know, can U.S. and China agree on this topic, or and so on. But a ray of hope is that, and it's ironic that some of the leadership, in addition to actually really coming from NGOs, there are a lot of tree planting projects now. And then you have corporations that are realizing that they can't have their business on a wrecked planet. So Coca-Cola, Nestle, plenty of other transnational corporations actually are developing a much more pragmatic approach to sustainability, of course, to sustain their bottom line, but they also recognize that without consumers to buy their products, so it's part of their sustainability strategy. And I know that sounds quite strange and dark, but that is the kind of stuff that's being talked about and planned on and with open eyes, and because with the Rhine River drying up in Germany, you know, you had the German, everyone's attention on this topic. And as the temperature keeps rising, the problem gets worse. It will become undeniable that we got to do something. And then it becomes a question, is it soon enough, and at what rates, and so on. We can act in our collective self-interest to manage this risk, because stopping point. But there's a reception after. We can have a drink and try to forget some of this. No, we can't forget. We've got to empower the next generation to help us. This is so great.
This is a token of our appreciation for coming.
I'm so glad that I came. It's a really charming college and town, so thanks for the invitation.
Yeah, thank you for coming.